Finally, we get to continuity. When is a function continuous? When is it not? Well, the easy explanation that is not mathematical is if you can drive your car across it, then it's continuous. Okay, that's a terrible explanation, but let's drive cars. Here we go. Up a hill, down a hill. Oh, no, we fell off a cliff. Discontinuity right here. We keep driving, going up a hill. Oh, what a pothole. Messed up our car. Discontinuity there. And then they're down, and oh, there's another one. Now, in this case, this is where the earth just vanished, and this is where the earth sank. Either way, we're going to have a discontinuity here, here, and here. That would be at x equals -2, +1, and at +3. We are going to go ahead and formalize that with a few other little things. We have different types of discontinuities as well. Getting ahead of myself, we have jump discontinuities. This is a jump. This is a removable because we would be able to very easily fix this, like if you can fill a pothole. Again, not the mathematical definition, but it works. And then there are vertical asymptotes. So let's slide up. You saw this notation briefly, but we are going to go through it a little bit more. Let me zoom out, raise the camera up some. There we go. And let's use what color? Let's go with blue. All right. The limit as x approaches -2 with a little negative up here, which means we are approaching from the left. We're going to approach -2. Normally I would grab 2 ink pens and I'd say, what's our y value? And I don't care. I'm approaching from the left. I only care about this one, and the y value for the limit is 2. This is 2. Now we're going to approach from the right. So we're not doing this, we're doing this. And the y value is 3. Oh, but the function doesn't exist at 3. I hear you, but what's the limit? What are we approaching? The y value is 3. Now we take the little plus and the minus off of the end of it, saying I don't care from the left, from the right, as long as they match up. And they don't. So this limit does not exist. Technically it doesn't equal, does not exist. And then I'm asked, what is the value of the actual function at -2? And the actual value of the function is +2, because that's where the hole is. Okay? We have already decided that there is a discontinuity there. So this is one of those situations where we have a discontinuity, and the discontinuity is because the limit does not exist. So I'm going to go ahead and just kind of slide up and down throughout this paper as we fill this out. It's going to look like that. You're going to get, neck problems as you try to follow along. A function is continuous when these conditions are met. Well, we have a discontinuity here because of a problem. Let's identify the problem. And if we can patch that problem, we'll be able to say, well, we have a continuous function when we do such and such. Okay? We have a discontinuity at -2 because of some reason. So if we don't have that problem, then we are on our way towards continuity. All right, what was the problem? The limit didn't exist. The limit from the left didn't match the limit from the right. And because of that, we had what we call a jump discontinuity. So a function is continuous when these conditions are met. And condition number 1, in no particular order, is that the limit exists. The limit as x approaches c for some function exists. And to put that in other terms, I'm going to put this in parentheses, I would say that the limit as x approaches c from the left, you've seen this before, equals the limit as x approaches c from the right of our function. And again, that did not happen here, which is why we had a discontinuity. Okay, we're going to have 2 more problems that define discontinuities. So we're going to go ahead and put some arrows just for fun. Let's go to the next one. We're going to approach 1 from the left on our function. So as we approach 1, x value of 1 from the left, our y value is 4. As we approach 1 from the right, the y value is 4. And therefore, the value of the limit, like true limit, both sides, do they match up? Yes, they do, is 4. And then the value of the function at 1 is, there isn't one. So this one's undefined. So if you want to get technical, it doesn't equal undefined, but it is undefined. Not necessarily to be confused with does not exist. It's different when something is undefined and does not exist. Okay, limits have the potential to not exist. Functions have the potential to be undefined. There you go. But the problem with this one, discontinuity, was that the function was undefined at some point. So if I want there to be continuity, then I better have the function to be defined at that point. So in order for me to have continuity, I better have a function that exists at some specific c value. So f of c is defined. I say it exists, that really means it is defined. Okay, let's move on. All right, I'm going to skip this next one, skip the next row. We're going to go to the bottom one with the 3's in it. We'll come back to that one. So the limit as x approaches 3 from the left. We're going to approach 3 from the left. The y value is 2. Done. All right, let's approach 3 from the right. The y value is 2. Done. Let's just approach 3. Not left, not right, both. Not just assuming it's one or the other, it's both. And the value is 2. And notice that this number of the limit always matches left and right. And it doesn't, the limit doesn't exist if left and right don't match up. Okay? What's the value of the function at 3? Well, that would be that dot, which is at 1. Okay, so we have a discontinuity here, and we have a limit that exists, and we have a function that is defined, but they don't match up. So in order for us to truly have continuity, we not only have to have a limit that exists, function from the limit from the left matches the limit from the right, and a function that's defined, we also have to have the value of that limit to be the same as the value of that function. We didn't have that here. We had a limit that was equal to 2 and a function that was equal to 1. They don't match up. It's that sinkhole in the middle of the road. It's that sort of situation. Okay, so let's go back and let's do this one. And this is going to be basically a series of questions that talk about what happens at x equals 2 as we approach 2 or plug 2 in or left, right, that kind of thing. So 2 from the left is a value of 3. 2 from the right is a value of 3. Therefore, the limit is 3. And the value of the function is 3. Notice that these were all the same. The limit existed, the function was defined, and the limit matched the function. Okay, those were the 3 conditions right there. All of those fell apart in the other examples, but in this example right here, we have continuity. At the very beginning of this video, we said we have discontinuity x equals -2, +1, and +3. But we do have continuity at 2 because none of those things happen at 2. None of what things? An undefined limit, an undefined function, a limit that doesn't exist, or where they don't match up. Okay? We've met all 3 of those conditions for x equals 2. So let's talk briefly about what a removable discontinuity is versus a non-removable. We talked about it at the very beginning, and I'm going to just sort of point at some things as well. This right here and this right here are removable discontinuities. And this discontinuity, which is kind of broken there, this is a non-removable. And again, the non-mathematical way of saying it is, I can patch this hole in the road. No. In this case, the whole road is washed out. Just start all over. Like, not going to happen. The cliff just fell. Like everything is gone. You drove up and there's no more road. Like that, you got a problem. Okay, so let's put this in mathematical terms. In a removable discontinuity, then we are going to have a limit that does exist. So let me write that down. We'll keep going with blue. So the limit as x approaches c of my function exists. And so here's my definition for it as well. F of c can be defined or redefined, like we could change it. Like if we could magically change the function at one point, we could, to create continuity. Okay, and let's go back up to the graph and look. We have removable discontinuities here and here because I could easily say, you know what, if f of 1 was equal to 4, fixed. If f of 3 was equal to 2, fixed. Drag that point up, fill that one in, we're good. Can't quite do that here. So non-removable discontinuity is where the limit as x approaches c of my function does not exist. And I'm going to go a little further and kind of put another sense with it like I did on the other one. So f of c cannot be redefined or even defined in the first place. Putting those words in a different order than I did up here. Oh no, not a big deal. Defined or redefined to create continuity. No matter what I define f of negative 2 to be, I'll never fix this.